All right, it's my great pleasure to introduce Marie Aubert from Institut de Mathématiques de Jussieu et CNRS, who will speak about the local Langlands correspondence from extended quotients to affine Hecke algebras.
Thank you so much for the presentation, and thank you very much for the organizer for inviting me. It's a great pleasure to be here and to have the opportunity to participate to this wonderful conference. So, okay, I will start by talking about extended quotient. So it's a very easy thing to explain. So I will first talk about extended quotient. I will define this in a few minutes. And then I will show you three kinds of extended quotient. And in particular, some extended quotient on the group side and some on the Galois side. And in this second part of the talk, I will pass to Hecke algebra. Which would be introducing Q in the setting. So, what are the main actors today? So, as in several talks before, F will be a non-Archimedean local film. So, I was very pleased to hear that it was on a TV show already. By the way, if you want a movie on the Goldbach conjecture, there is also one in France. But let's go later. We will refer to G as a p-adic group, and I will denote by G check the Langlands dual of G, so meaning the complex reductive group, which would then dual to that of G. So here are a few examples. So G, GLN over QP. The Dinkel diagram show you that the root and goals can be identified, and so G check is GLNC. If you look at SLN QP, in fact, you get PGLN or PSLN over C, and the same thing for the other way. And for symplectic orthogonal, you get the odd special orthogonal, and vice versa. And for the even orthogonal group, it is autodual, self-dual, and same thing for G2. Okay, so these are just examples. And what is the local Langlands correspondence? Again, you have this already in several talks before. So just say that it, at the moment looking at the classical local Langlands correspondence, and with the hope that one day it will become more geometric. And it predicts a surjective map satisfying several properties. So on the left side, I will consider isomorphic classes of irreducible smooth representation of my p-adic group G. Smooth means that I have a topology on the group, which is inherited from the one on GL over F, itself coming from the p-adic topology over my p-adic field F. And smooth means that any element in the vector space of my representation has its stabilizer open. And so it's surjective map, which is going to these things, which is again classes up to G-check conjugacy of L parameter. L parameter are certain homomorphism from the Weidelin group, which I like to view as a WF cross SL2C with value in the L group of G. So here WF is the absolute Lie group of F, which is a dense subgroup of the absolute Galois group of F. And LG is just there is a natural action of WF on G check and can define this group. But if a group G is an inner form of a split group, then this symmetrical product is actually a direct product and you can forget about WF. The main thing is that the fiber of this map, which are called L packet, are expected to be finite. So for GLN, the conjecture is known, and the fiber are just singletons. So it's actually so the map L is a bijection. But already, if you go to SL2, and you have seen this, for instance, in Engo talk yesterday, you see that the fiber you can in SL2 you can have a packet with one singleton packet with 2 elements, and also packet with 4 elements. Okay, so if you want to have a bijection, you need to do something to promote that map L into a bijection, and to do that, you will consider the notion of enhanced parameter. So you will enhance the parameter phi by some object rho, which is an irreducible representation of a certain finite group attached to the parameter phi. So I will give more detail later. And then we denote by phi E, so E is for enhancement, for the set of G-check conjugacy classes of enhanced L parameter. And we also choose the word enhanced because it's also with the E in French, because you can say enrichi. Okay, so adjective, actually there are more reasons. The better reason which is come from a work of Asher and his collaborator regarding an enhancement attached to the Springer variety. So the adjective Langlands correspondence was constructed in particular in the following cases. So of course for GL1 overhead, classified theory, a long time ago. For GLN by Alistair first, and the simplified proof by Enya, and the different proof by Scholze. And then for SLN, so first by Iralda and Saito when F has characteristic 0. And we extended it in the case of F has characteristic, positive characteristic. So for SLN, when F is a finite extension of QP, of course, the proof uses Hecke Langlands. First, it is for inner twist. So inner twist, we use Hecke Langlands correspondence. So we first do it for GLM over G, where D is a division algebra. And then we use the restriction of a representation of GLMG to SLM. And for inner form, it is rather certain in the sense that the restriction is not necessarily, does not have always multiplicity 1. And what we did with, what I did with Baum, Kleiman, and Solovel was to extend this to positive characteristic. And so I'm pleased to, again, in many talks, I can use the name of Gajdan. So to do that, we use the Gajdan method of closed form to pass from characteristic 0 to positive characteristic. Then for SP2 and for classical groups, we have the work of Arthur in characteristic 0. And for G2, we constructed a bijective correspondence with Lucci using the method I will develop later. And there is also different proof by Gan and Sabin using data correspondence, which show up roughly at the same time. Okay, so what are extended quotient? So in the it's a notion which I heard from Paul Baum and Roger Kleiman. And at the beginning, it was what we were using was something we called geometric extended quotient. But when we started to think about the relation with that and Langlands correspondence, the canonical one, I mean, the one which gives us canonical result was the spectral extended quotient, which is this one. So I take a space X and a finite group acting on an X, and I denote by gamma X the isotropic group of X for any for an X, an element of X. And then the spectral extended quotient is just the quotient. You consider the following space, like a pair of elements, X in X and tau, an irreducible representation of gamma X. Of course, gamma is acting again on this set, and you consider just the quotient, that space by gamma, the usual quotient. Okay, the more better way to think of it is as an inertia stack, as David talked to Paul many years ago. So here are two examples. So first one, I will take a torus in a reductive G, and I will consider for the group gap. So X will be the torus, and the group gamma acting on X will be just the Vi group of G, and G of T mod T, acting by conjugation. And then we can do the definition that I just gave, and you have an extended quotient. The second example, which will show up soon here's the following. So I take a p-adic group and L a Levi subgroup of G, and I consider the set of Ir cusp of L, which is the set of isomorphic classes of supercuspidal irreducible representation of L. Then instead of taking the Vi group, I consider something called sometimes called the relative Vi group, so WL, which is LGL mod L, which is acting on cusp of L. So the space here will be cusp of L, and the group will be WL. And then you can again form with corresponding spectral extended quotient. So I like to call it panoramic to distinguish from other extended quotient that we'll show up later. And panoramic means that for LAVL, I consider all the supercuspidal irreducible representation of L. Okay, so now I would like to cross the river and to go on the other side of correspondence. So L, I will consider two complex dual group, the complex dual group of G and the one of L, and a certain set of elements, set of L-check conjugacy classes of certain objects that we call cuspid of certain enhanced L parameter for L. But in the same way as on the group side, I would like to take only the supercuspidal representation. Here, I just want certain enhanced L parameter, which will be qualified as cuspidal. And I will try to explain later what they are. And and we have a property that, again, on this side, the normalizer in G-check of L-check mod L-check acts on this space of conjugacy classes of cuspidal and enhanced L parameter for the Levy. And so again, I can consider the panoramic spectral Galois extended quotient as the quotient obtained by these two spaces. On the other hand, the group is easy to check, but WL and WL check are canonically isomorphic. So this leads us to a conjecture which is a weak version of a conjecture we will see later, which was formulated by Ahmed Moussaoui with Ahmed Moussaoui and Martin Solovel. This conjecture says that these groups are canonically isomorphic, and we conjecture that the local Langlands correspondence actually induce a bijection or possible canonical bijection between these two extended quotients for any Levy L. Okay, so this is a conjecture. And what I will do now, I will try to explain to you what are these objects on the Galois side, this cuspidal and enhanced L parameter. And then I will explain to you how we can refine this conjecture in a natural way. Okay, so what is the way to, on the group side, it's well known, and it was very well explained in Charlotte talk over final field, and it's exactly similar for p-adic. We have parabolic induction, so we start with a supercuspidal representation of a Levy, and you extend it trivially to the unipotent radical of a parabolic, you induce. And so any smooth irreducible representation occurs as a subquotient of such induced representation. And moreover, the pair formed by the Levy and the supercuspidal up to G conjugation is uniquely determined by the starting representation. And this pair is people in p-adic representation call it the supercuspidal support of a representation. And if you think more, if you prefer real Lie group, it plays the role of the infinitesimal character. So we would like to do something similar on the Galois side, and to do that, we need a tool to replace the induction and the restriction and the supercuspidal map. And this tool is given to us by the generalized Springer correspondence. Okay, so let's explain briefly what it is. So now I forgot the previous setting, and we just so I consider a group that I will call curly G, which is a complex reductive group, and it may be disconnected. In many situations, it will be disconnected. And then I take a parabolic subgroup of G. So what is this? So I need to explain because the group, if the group is disconnected, so it's just a subgroup of G with, oh sorry, this is a curly G, it should be a curly G. a subgroup of G such that the identity component of P is a parabolic subgroup of the identity component of G. Then I take L complement in P of its unipotent radical, which is the unipotent radical of P naught. And I denote by unip of G, the unipotent variety of G, or if you prefer, you can take the unipotent cone similarly. And same because we are in complex field. And same thing for P and L. And then I will consider the category D, B, C of X of bounded constructible L shapes on an algebraic stack X. And with this notion, you can define the analog of parabolic induction. So it's very similar to the, I mean, it's what you have seen in, I think it was also in Charlotte talk in his construction for, whenever she was explaining how to construct a geometric version of parabolic induction for p-adic groups. So here you take unip L, the quotient of stack, so unip L mod L, and you have a natural map, a projection map from unit P mod P, which is given by the natural projection from a parabolic to its levy. And again, and similarly, you have a natural injection of a parabolic into the group G, and this gives us a map iota from unit P mod P to the quotient stack unit G mod G. And then you define the functor as usual. So you take P star, and you compose by iota lower shape. And the point is that this, you have all the property you want. Transitivity of induction and a notion of cuspidality. So an object will be cuspidal if it does not occur in a proper induced map like this. And Mackey formula, I mean geometrical lemma. Okay, so so in particular, so what I just said, we have a notion of cuspidality, and moreover, we can describe precisely what are the cuspidal objects. So first, the simple objects are all given by as intersection homology shift over a unipotent class C, and E is a irreducible local system on C, and among all these simple objects, we have one which are cuspidal, and so you say that the pair is cuspidal if the shift, the IC shift is cuspidal, in the sense that it does not occur in a proper parabolic induced object. Okay, so now we have this, and what we would like to do is use this in order to construct local Langlands correspondence. And this was an idea of Ahmed Moussaoui when he was doing his PhD with me. His idea was to consider a certain group. Okay, just a second before saying what this idea. First, when you wanted to look at the Langlands correspondence, and if you are considering a group G, which is a pure inner twist of a quasi-split group, the natural group to consider is the centralizer in G shape of the image of W prime F. If the group is not a pure inner twist, there are variants of this for rigid inner twist, for instance, which works similarly. Okay, so we have this group, and the irreducible the element of a packet, if you consider not just one packet, but all the union of the L packet for all the pure inner twist of G, this union of packets is expected to be naturally in bijection, with the irreducible representation of the group of component of that group. Okay, I was on the way to say naturally. You need first to fix the Whittaker data. Okay, so then what an enhanced parameter, so now I can give you the definition, will be just a pair, phi rho. Phi is an L parameter, and rho is an irreducible representation of that. So the enhanced parameters are expected to parameterize the union of packet for all the linear trees. And if you want just one for your group G, you will fix the restriction of rho to the center, and we get a character, and using like this isomorphism, you can fix attached to your group. And in particular, if the group is simply connected, and if you are just interested in the quasi-split group, we'll just take all the characters, this enhanced parameter, which was the one which occurs in Roman talk last day. Okay, so now this was the idea of Ahmed. So it was the idea was to consider not the image, so not the entire image. So SP was the image, the centralizer in G check of phi of W prime F, but just the centralizer in G check of the image of WF. And if you take this group, but then it is easy to check, and you fix a unipotent element U, which is by definition the image by phi of the stand of 1, the standard unipotent element of cell 2. Then it's just an easy application, easy computation to see that this group S phi is canonically this component group S phi is canonically isomorphic to the group of components of a centralizer in G phi of U. So now we are very happy because we have the unipotent, you have a group. Okay, it's maybe disconnected, but anyway, complexly grouped, and the unipotent element of that group. So when we are in that situation, we have, if a group was connected, we have a general Ashkenazi correspondence, which is due to Lustig, and then for disconnected group, we were able, to extend it. And then we can define what is a cuspidal enhanced parameter. Of course, I mean, beyond that, we have the idea that it should be related to supercuspidal, so the parameter should be taken to be a discrete one, meaning that its image is not contained in a proper Levy, and the pair, the conjugacy class of U phi and rho, rho is a cuspidal pair in this group curly G phi. Where you use the definition that I've just given before for a group curly, I mean, arbitrarily disconnected reflective complex group. And then the conjecture, which is the which was stated with Moussaoui and Sullivan, which is the strong version of the previous one, is that irreducible cuspidal. It's not it's related, but it's different. There is a canonical, the local Langlands correspondence very strict to a bijection between the irreducible cuspidal, supercuspidal representation of G and the cuspidal enhanced L parameter. So a priori it would be very strange why these things could work, because I mean, of course, both have cuspidal object, but the setting is very different. But in fact, it works in many cases. So Moussaoui in this thesis proved the conjecture for general linear group and split classical p-adic group, meaning SP and SO. Later, we check it for inner form of general linear group and special linear group, and also for quasi-split unitary p-adic group with Moussaoui and Sullivan, and with G2, we prove it in the case of G2. And more recently, we also prove it with Moussaoui and Sullivan in the case of all pure inner forms of quasi-split classical p-adic group, including G-split. And of course, in the last, for classical group, we are using even the work of Harper and also the work of Colette. Okay, this was the situation. I mean, this is the state of art in the case of cuspidal object. But of course, cuspidal, supercuspidal are not enough. You would like to have all the smooth irreducible representation. And to do that, you will define a cuspidal support map and try to use, to build from that a correspondence if we have this conjecture on the Levy. Okay, Okay, so I will phrase it in like this. So I will assume that I will call something as property C of L. C is so I will fix a Levy L, and the property is that there exists a bijection from here cusp of L to the space of cuspidal enhanced L parameter, which is equivalent by the action of a relative variable, meaning exactly this. So L composed with the L of W is equal at W check composed with L sub curly L sub WL, where I denote by V check the canonical bijection evocated before between W of L and W of L check. Of course, the cuspidality conjecture for L exactly says that property L is true where LL is the local Langlands correspondence. So, just as a remark, the cuspidality conjecture is equivalent to property C of G is satisfied with LG equal LLC. Okay. This a bit strange way of phrasing it is because I do not want to assume the conjecture. So now, if a property CL is satisfied for L Levy subgroup, then it's easy to check that it induces a bijection between the corresponding spectral extended quotient. So this is, I mean, just the property is made to have this. Okay, so now what we can say. So first, we would like to study the set of enhanced L parameters, and to study it, you would like to decompose it in several series attached to pairs of Levy and the Levy and the cuspidal representation of Levy, cuspidal enhanced L parameter. And so this is the first thing that we obtain, that we have a partition of phi of E. So if in many cases, it's just a partition of over all the Levy of G up to conjugation of a partition into extended quotient. Actually, when we were looking at inner form of SLN, we realized that it was not always true, and that sometimes there is a two co-cycle which non-trivial two co-cycle will show up. So it's a twisted extended quotient. I will not give a definition, but in many cases, this co-cycle is twisted with string, but not always. So this was on the group Ogawa side, and independently on the group side, Soloway proved a similar result. So a partition of E of G, so the conjugacy class, isomorphism classes of smooth irreducible representation of my p-adic group G, as an union of, again, twisted extended quotient. Okay, so we have these two results. And now if the natural consequence, obvious consequence of these two results is that if a property CL is satisfied for all the Levy of G, including the case where L is equal to G, and if the bijection, okay, the bijection is this one. This bijection is compatible by twisting by two co-cycle, which in many cases is true because two co-cycle are just trivial. Then we get a bijection between E of G and phi E of G. So now, okay, we are happy we have a bijection, but then is it the right bijection? Is it local Langlands correspondence? And in many cases, we were able to show that it is indeed the case. But before going into that, I will explain a stronger version of this, so which we will use a smaller extended quotient. So the idea is, here, I would like to have a bijection like this, and I get the bijection here if I using these two bijections. So this is a decomposition of my space as a partition on other space of subspaces, and same thing here. And I like to view this as a decomposition of this into a certain object with some color, and here also. And the way to match them is to say that the object, if I take if L is a given color, so the object attached to L are in bijection with the object attached to L here. But as I said in the beginning, this extended quotient here is made by taking all together all the supercuspidal representation of L or all the cuspidal and L parameter for L. So I have something blue, but I would like to put it in bijection with some with the other side also blue object. And what I will do now is that I will find some shade of blue. I will define my blue in different a more precise color, and then same on the other side. I will try to match this the light blue with the light blue, the dark blue with the dark blue, etc. Okay, sorry. But for me, it's
The red.
sorry.
So in the mirror side, there was this red, like in the Soil's theorem, there's.
Bit is to say that to have a true statement, we need to twist by two cocycles. So this red thing is a twisted extended quotient, and actually it's a family of two cocycles, one for each L. Thanks for the question. Okay, so now to color in a better way my object, I will use the work of Bernstein. So Bernstein has defined this for us, so it's a Bernstein center, and so Bernstein has obtained, constructed decomposition of all the category of smooth representation of an arbitrary p-adic, and it goes as follows. So I will denote by X and R L a group of unramified character of a Levy. A character is called unramified if it is trivial on every compact subgroup. And instead of just considering, so if you were of a finite field, you would just consider G conjugacy class of a Levy and a cuspidal representation of a Levy. And here I will do almost the same, but a slightly weaker condition, because I will allow, so it's why I put bracket here, I will allow to twist the supercuspidal by an unramified character of X of L. So if you prefer, this will be just the G conjugacy class of a pair formed by L and the orbit of sigma under the action of a group of unramified character of a Levy. And then we can consider the set of isomorphic classes of irreducible smooth representation of G, which have a property that their supercuspidal support lies in this S. So the supercuspidal support is L sigma tensor chi, where chi is unramified. And also we can consider the element of unramified character which stabilize sigma, and consider the quotient of XNRL by this by XNR and sigma. And this is and the map with sun chi to chi tensor sigma tensor chi gives you a bijection from this quotient to S of L. And this this is very nice because it's endorsed LS with a structure of a complex torus. But be careful, it's a complex torus viewed as an algebraic variety. And the group structure, if you want to have a group structure on it, you will need to fix a base point in SL. Okay, and then you can consider again a group. So before it was when I would like to take all the group together, I was considering NG of L mod L. Here I want to be more precise, and I will consider just the element of G which fixed L, but also the orbit of a supercuspidal. What I denote by NG of S mod. And so this group occurs in Bernstein work, and it is a finite extended Weil group, meaning a finite Weil group, a semi-direct product with a finite abelian group. And this group acts on TS by automorphisms of algebraic variety. Okay, and then we denote by B for Bernstein the set of such classes S. And now with this, we have the decomposition of a partition of E of X, more precise than before. I mean, where I just here I take the joint union of the E SG. And then what we was okay on the group side, Solovet shows that E S of G is can be in bijection with the twisted extending quotient of T. That is of T mod WS. So I should have a double slash. An example, if you take an example of this Bernstein series, if you take for L torus, F split maximal torus, and for sigma just a trivial representation of G, then this subset S1 is the set of Iori spherical irreducible representation of G. Application. Okay, so okay, see, this was to give you a rough picture of what we have on the group side, and the slogan is now something similar, exactly similar should work on the Galois side. Okay, so I will not spend too much time on it, but it's exactly the same. So we take the dual group. We have also a notion of unramified, to assume that the group is split to simplify. Then the unramified character on the Galois side will be just the morphism, which are trivial on the inertia and with value in the identity component of a center of L check. And again, we take the action of the orbit of a cuspidal enhanced L parameter by that group of unramified character. And this is what we denote by S check, and we consider the enhanced L parameter whose support cuspidal support lies in S check. So I didn't tell you what is how we define the support cuspidal support of an enhanced L parameter because I do not have time. And to do that, you use I mean, it's something that we have already for in the case of generalized Fourier correspondence, and you just transport it from the group G5 to the space of enhanced L parameter by using the Jacobson-Morozov theorem. And again, we can consider the group which W S check with normalized L check mod L check and call B check of G this element. And then again, we have a decomposition which is parallel to Bernstein decomposition, but on the other side, we say that phi E of G is an union, the adjoint union of phi E S check of G. And okay, then we also have a second result, which says that this space, this subset is canonically in bijection with a twisted extended, with the corresponding twisted extended quotient. Okay, so it's really the same story, a parallel story, I would say. I think so. It's very nice, but the point is that Bernstein does something more. It does not just give us the decomposition of a partition of irreducible object, but the decomposition of a category. And it's what we are using now. But before that, I will still give some, would like to state a theorem. So if I take in the following, so we expect that something in this spirit is always true. But let's be more precise. So assume that G is an inner form of GLN, or the exceptional group of type G2, or a pure inner form of a quasi-split p-adic, classical p-adic group. Then we can define a map, a bijective map. So you fix S, so one element, one Bernstein component, and we need to attach to S a certain S check. This is very important because to state something, I mean, it's not for arbitrary S and H check. S and H check have to be related. And so what we would take for S check, you can guess what it is. You will take, of course, the Levy's F check, WF, and then instead of sigma, you will take its image by the local Langlands correspondence for sigma. So this explains what we have these cases, because it's cases where we were able, or we know we are already in literature, or we were able to do it, to define the Langlands correspondence for supercuspidal of all the levy of G. And if we have that, then we have a bijection here, which is the one I just recalled before, on the group side, and we have a bijection here on the Galois side. And these two we have seen, and okay, in these three cases, there is no cosine. All the cosine, we know that all the cosine are triggered, so no need to twist. So we have this, and this map coincide with the local Langlands correspondence, and moreover, the following diagram is commutative. So this following diagram is looks like this. So here we have one Bernstein series. You consider the supercuspidal map, and we arrive in here SLL. We do something similar in the Galois side. So here we are on the cuspidal word for the levy. Here you have Langlands correspondence. And here we are G, and we also have Langlands correspondence. Okay, but then some remark. In the case of in the case 1 and case 3, we have already at our disposal Langlands correspondence, so we use it and we check that this diagram is commutative. In the case where we on the exceptional group of type G2, we do not have Langlands correspondence, just in some cases. But we use this diagram as a property expected to be satisfied by the local Langlands correspondence. So we use this as an input of our construction of the Langlands correspondence. Okay. Okay, so I was saying a bit too early that Bernstein did more than just looking at the irreducible object. And in fact, he proved that the category of smooth representation of G is a direct product of full subcategory. And the irreducible object of RSG, R here S, the one which we called before here S of G. And what we prove on the Galois side, we were able to construct and possibly twisted, extended affine Hecke algebra attached to G check, S check, or any S check. And this extended affine Hecke algebra has a property that is a natural bijection between this set of enhanced parameter of G with cuspidal support in S check, and the simple modules of this affine Hecke algebra. And on the other hand, what I can say? Okay, now in the case where G is an inner form of GLN, on the three previous cases, then it is also true that RS of G is Morita on the group side, but RS of G is Morita equivalent to the category of module, there is an equivalence of Morita between these two categories, where here is the category of modules of a certain affine Hecke algebra, HGS, which is on the group side, and these two, these two Hecke algebra are actually canonically isomorphic. When I say that they are isomorphic, of course, I'm assuming that S check is obtained by S by the local Langlands correspondence. Okay, so in general, we do not expect something exactly like this. You will have to replace Morita equivalence by something a bit weaker, because for example, inner twist of SLN, even for SLN, this will not work. But what we expect is that there is a Morita equivalence, an equivalence between the representation of finite length of G and corresponding module of the equation. But this would take me too long to explain, so I will not enter more in this. But I will give you an example of the application of the Bernstein decomposition, an important case, which is the case of the group of big Hecke algebra itself. So we have already seen this algebra with maybe other names previous talks. It's just a convolution algebra of locally constant compactly supported function from G to C. And you can, and when G is acting, we can consider the group acting on it by left translation. So you get an algebra by using the convolution product. And so you have a representation of this algebra, and then you can apply Bernstein decomposition to this representation. And you get a decomposition of this big algebra as a direct sum of two-sided ideals indexed by the S in the G. Okay, why I like this is for, I would say, several reasons, but one of the reasons is that we can, from that, pass to the world of sister algebra. So when we know that from the point of view of non-commutative geometry, in the case of when you look at temporal representation of G, it is interesting to consider the reduced sister algebra of the group, which is defined as a completion of H of G in the algebra of bounded linear operator on the Hilbert space L2 of G. And we know that the spectrum of this reduced sister algebra coincide with a temporal dual of G. And to see that, you can pass to the Schwarz algebra. And considering the previous decomposition of H, we get a similar decomposition of a sister of G as a direct sum. And why it is nice? Because if you heard about the Baum-Cohn correspondence, in Baum-Cohn correspondence, there are two sides, and the map, which is the assembly map, going from one side to the other. And the side which is the most mysterious is the side where we have the K-theory of the sister algebra. And here we are decomposing this in blocks, in some parts. So in some sense, we are refining one part of the Baum-Cohn correspondence. And we can make this more precise. So you have the following conjecture, which can be viewed. So, okay, in the background of all of this, there was ABPS conjecture, but I did not have. Right? And B is for Baum, P is Pleiman, and S is Sullivan. And this is the topological K-theory part of the ABPS conjecture. And it says the following. So we fix S, Bernstein inertial class. And so we consider, because we are interested in temporal representation, we consider the set of unitary representation in our Bernstein torus TS. This TS and is for unitary, is a compact real torus. And then we expect, we conjecture that there exists a canonical isomorphism between the classical topological equivalent K-theory of TS unitary, with value in the K-theory of a sister reduced, the part of a reduced sister algebra which is attached to S. We do not have yet a proof of that conjecture in general. We proved it a long time ago up to torsion for Iwori spherical representation. And probably it's possible to extend it to all unipotent now. But the thing which I found interesting is now we understand better if the conjecture is true, if we believe in the conjecture, we have a good understanding on how to view the K-theory of the sister algebra. But now the other side of Baum-Cohn, if we have a decomposition on this side, I'm playing the same thing. I have color on one side, I will put color on the other. When I did it for Langlands, I would do it for Baum-Cohn. So now I have my color on here, and I would have put color on the other side of Baum-Cohn. And I don't know, of course, if we have the assembly map, if we know an explicit description of the inverse map of the assembly map, then you will get something on the other side. But it's natural to think that there should be something, possibly to define something directly. And we worked on this with Pleiman some years ago, and we were able to do something for GS3. But he did it something already with Ixon and Baum for SL2. And we did it GL3 that after effect of that any other result. Okay, so sorry, I forgot one thing. Okay, so for classical groups, and it will be the last part of very last part of my talk. In the case where the group is classical, we can say more about this CR star GS. It is Morita equivalent to reduce the C star completion of HES, which means the closure of HES in the algebra of bounded linear operator or the Hilbert completion of HES. In fact, it's not just for classical group, it's possible to do it more, but there is no general statement. I mean, with a list of conditions, there are some results by Sullivan which show this, and in particular, it shows it for classical groups. But this opens the door of the following, is that we can use what I have just explained to study the how correspondence. Okay, maybe something very old, which relied to my PhD thesis. My PhD thesis was to the subject given by Vasturge was to study, to describe the how correspondence for Iori spherical representation in terms of characteristic parameters. So this, in some sense, is a generalization of that, but as you will see, is just the beginning of a generalization. So I take a dual pair, a symplectic group and an orthogonal group, but I take even orthogonal group, and I fix an S. And then first, it's easy to check that the image of the how correspondence for all the representation pi in one Bernstein, in the Bernstein block defined by S, belong to a unique Bernstein series on the other side. So this is just an application of an old result by Kudla on the description of the data correspondence. And then when we have this, you can use what I have just described and deduce that we can view the how correspondence between G and G prime as, if we fix S as a correspondence between simple modules of extended affine algebra, of the extended affine, corresponding extended affine algebra. So H, G, and S, and H, G prime, theta S. And this, by using what I explained before, you will get a correspondence between the corresponding Galois object. Just one remark, which is goes back to Kudla's paper. So theta S is defined using the first occurrence of a representation. It is totally explicit. But now, if you assume that n is okay, there is a confusion of my notation. No, it's n prime. Yeah, this n should be an n prime. So when n prime is n or n plus 1, then the theta correspondence preserves temperedness. I mean, some tempered representation to other one, which is not true in general, but it's true in this case. And so the theta correspondence induces a correspondence between simple modules of this C star algebra blocks. And this, the interest of this is that recently, 2 years ago, there was an interesting work by Meland and Sangun, in which we constructed using Riffel induction for group of almost equal rank like this, but unitary groups. They constructed a module using Riffel induction, so the C star algebra world, which encounts the data correspondence in this case. So we hope that there is some relation with that. And of course, the next step will be to describe more precisely that bijection. And okay, there were no physics at all in my talk. It's not true. And okay, There is some work in progress by three physicists. So Johan Henriksen, who is at the moment at a PhD Saclay, so close to Paris, and with Anatoly Dimarsky, from the University of Kentucky, and Brian McPeak, McGill, and what they are doing, they are we are studying CFTs to perform partition functions, which are generated by error corrected codes. Attached to a dual pair formed by a symplectic group and orthogonal group over a finite field. And last month, Johan wrote to me asking a question, very precise question on an old work I did with Michel and Rouquier on the description of the theta correspondence over finite fields, because we wanted to use the precise description of a theta correspondence in order to obtain a description of this function. So I don't know how they will made it and what is the story. Yeah, and I hope that I will have more development in the future. Thank you very much for your attention.
Thank you for your very colorful talk.